Hello, this is section 6.3 for Calc Survey, and today we'll be talking about the fundamental theorem of calculus to find definite integrals. And we've talked about the fundamental theorem of calculus, but we didn't know how to do antiderivatives yet. And now that you've been introduced to how to find an antiderivative, now you can do that all-important middle step here, where you need to find the antiderivative before you plug in the upper and lower bounds. Sorry about that line right there. So, and notice we need the original function in order to subtract. So we have this little middle step here where we find the antiderivative, and we put a bar here, and we indicate the upper and lower bounds, and then we can plug in f of b minus f of a. All right, so it's a bit deceiving. It looks like, oh, I can just immediately jump to here, but there's a really important step where you do have to find the antiderivative. Okay? All right, so let's try one of these. So compute the definite integral. Now, I know you can use your calculator to check all these answers, but there's going to be many where it's going to say give the exact answer, or on your IU exams, they'll put an arbitrary variable, so don't get too dependent on your calculator, but it is a good way to check yourself. All right, so we are going to, in order to solve this definite integral, and it's definite because you have bounds here, first you have to do the antiderivative. So 3 turns into, as we learned in the last section, 3x. Now you might say, Cogswell, where'd that plus c go? Well, you can see when you do f of b minus f of a, both of those would have a plus c with them, so the c ends up canceling out. All right, so we don't have to worry about the constant. So you do the antiderivative, and then we draw a bar here, and you put your bounds 2 to 7. And then you simply do 3 times 7, so you plug in the upper bound, minus, then you plug in the lower bound, subtract those two, and there is the answer. Now remember, 15, that's the area under this curve, or the derivative, the function. And it's, in this case, it'd be a horizontal line from 2 to 7. Okay. All right, so we do the same thing here. So negative 3x plus 4 is our integrand, so we're going to do the antiderivative of both of those terms from 2 to 5. Now, it's not a bad idea to put parentheses here. I think you're safe without them, but if you want to be a little more safe, you could put parentheses. Some teachers might be a little bit pickier about that than others. But you know, we've found the antiderivative, so now you're ready to plug in the upper bound, which is here, minus the lower bound. And of course, you're plugging 2 into a binomial, so be very careful with parentheses. Just watch out. And then definitely use your calculator to help you finish that. Now, something really important. In the last section, in 6.2, the answer was an expression. This is an antiderivative plus c. That's the antiderivative. What we're doing in this section is we're actually finding the area under the curve with given bounds. So you're actually getting a numerical answer. So that there's a big difference in the type of problems you're dealing with. Okay, so then on this one, now in this case, just clean this up a little bit. I moved the 1/3 out in front, and then we're ready to go. So do the antiderivative, write your bounds, and then just don't forget that scalar. Leave that scalar out in front. And yeah. Now, problems 4 and 5 we'll come back and revisit. Notice I put section 6.6, and this is a section 6.6 problem. So we'll come back to those, and we'll do those in class. All right. You just need a technique called substitution, which you're going to learn in section 6.6. All right, problem 6 here. So this is one where you'll want to distribute the x. Well, you'll want to square it out, then distribute the x. You're just trying to make your life a little easier. So now you're able to actually do the antiderivative of each term. So we did that, and then wrote our bounds over here, and then last step is to plug 2 into the entire antiderivative, minus, and then plug -1 into the entire antiderivative, and then subtract. Okay, so as you can see, this section's kind of just another section for you to practice doing the antiderivatives. It just has that one additional step where you have to plug in the upper and the lower bound and subtract. So like here, sine, what comes before sine? Well, sine, cos, minus sine, sine. Negative cosine comes before sine. So that's the antiderivative. But then because it's something other than just x, you have to divide by the slope. And that only works when it's a linear function, by the way. All right. So we divided by 4. And then here's the upper and lower bounds. Put the bar 0 to pi over 4. And then your last step, this is the additional step. You plug in your upper and then minus when you plug in your lower and then get your answer. Okay. And there's just another example. Now, with absolute values, you will have to break up the indefinite integral. And you'd have to do this for the, well, I wouldn't ask you to do for an indefinite, but for a definite integral, I went ahead and graphed it. So technically, you would have to divide by 2. You can use your graphing calculator to graph this, but technically, if you factor a 2 out, that's where you're shifting it to the right 1.5. It has a slope of 2, so up 2 over 1, up 2 over 1, or left 1. So this is the graph of your absolute value, and you can see we're going from 0 to 3. Now, what this pink line represents, that's the part of the graph. If those absolute values hadn't been there, that's what the graph would have looked like. So this being the original function before the absolute values right there. And what the absolute values is, it took that part that goes below the x-axis and it reflects it, makes it positive, and that's what's creating that V shape for us. So when you go to rewrite the definite integral, you'll notice the part to the right of 1.5 wasn't affected at all. So that in that part, notice it's just the integral from 1.5 to 3 of the regular function dx. But the first half, that's the part that got reflected. So this part of the function, we have to put a negative in front, because what happened was all these values were negative. So we put another negative in front to create that double negative, making it positive. So that's where that negative's coming from, to get it to turn these values positive. And that's the part from 0 to 1.5. So I know that's a little bit confusing, but you will need to graph these to visually help you see what, first of all, where is the V, where is that vertex point, and then which part do you need to negate to create that double negative, which gives you a positive. Now from there, now you can do the antiderivative, the fundamental theorem, and then go from there, okay? All right. Last thing, improper integrals, so is when one or both of the limits is infinite. So you can see down here, show you a good example. No, right here, sorry. There's the infinity. So when you go from 1 to infinity. So sometimes you'll be able to solve these, sometimes you won't, depending on if it's one that converges or diverges. So, and you cannot use the fundamental theorem of calculus because infinity is not a number. The fundamental theorem of calculus deals with numerical bounds, and infinity is actually a limit. What are you approaching as you go off to infinity? So evaluate the following. So you could use your calculator to do these, or you can do the antiderivatives and the fundamental theorem. So you'll see you get 0.9 from 1 to 10. From 1 to 100, you get 0.99. From 1 to 1,000, you get 0.999. So you can easily see that you're approaching the value of 1, right? So what do you notice? The upper limit of integration tends to infinity and the area tends to be 1. So this is an example of an integral that converges. The area is finite, the limit is a finite number. And that's what we just saw. Now, what happens if it doesn't? So an integral that diverges is when the area is not finite. So I just made up a random example. And I showed you down here, and you go from 1 to 100, you get 18. 1 to 1,000, you get 61.2456. 1 to 10,000, you get 198. It's just getting bigger and bigger and bigger. It's not approaching a number. So that's an example of a diverging integral. Okay, so excellent section for you to continue the practice of those basic integration rules. It just has the extra step of using the fundamental theorem of calculus to get a numerical answer, right? But please do your homework and let me know if you have any questions.